All right, we're going to start our review of E&M today. So this packet reviews the entire class. We're sort of just going to speed run through everything. I tried to include the most representative but important examples for everything. So theoretically, there's nothing you'd see on the test that isn't a sibling of one of these questions. So today we're going to start with just the circuit basics. So that's everything with circuits that doesn't involve capacitors or inductors. So we'll just start. The first thing we did with circuits is we talked about electric potential and coloring it. So what are the rules for coloring electric potential? Well, we said that the positive battery terminal, we always colored red. The negative battery terminal, we always colored blue. And we said that color spreads out along the circuit. It explores all paths until the color hits something. And usually what these barriers are, they're resistors most commonly, or capacitors or inductors. They're open switches, and they're also lit light bulbs, or bulbs that are in a complete loop. And the greater the color change, the brighter your bulb is, or the greater the power dissipated. Because your maximum power would be created when you have your entire potential difference of the battery red to blue. And sometimes you get intermediates. So let's show that. So we're going to color each of the following circuits. We have one bulb in a simple circuit. And again, what is a simple circuit? Well, a simple circuit is literally just a battery and a bulb. I think we'll color everything at the end. Two bulbs in series. Well, what does series mean? Series, of course, just means there's exactly one path. I just tack on an extra bulb there. Two bulbs in parallel. Well, if series is one loop, then parallel must be multiple loops. And then what is a short circuit? So this one, I'm just going to start it off by just creating a simple circuit. And our best description of a short circuit would be a complete circuit with a light bulb, or anything that for that matter. It looks like a complete circuit, yet the device is not being powered. And that can be achieved, we said, by if you somehow give the battery a zero resistance path. So we used our little drive-through analogy, or our traffic lane analogy, that said if you open up another lane, customers will go down that lane. And it's not going to be all of the people go down the new lane, unless if you create a zero waiting time lane, which is the case of a wire. So that's why a short circuit behaves different than just a parallel circuit, because in parallel, there's still waiting time for both of the lanes. So you get a current splitting, maybe unequally, but you still will get current in each. So if we color code, our first rule says that the positive terminal of the battery is our highest potential point in most circuits, unless if we have some weird multi-battery idea. I'll color the first three, and then we'll deal with the short circuit case, because that one's kind of strange. And then our lowest potential is always this bottom terminal of the battery. So that blue also explores all available paths. And now if we're out of colors, which we are in the series case only, we have to add an additional color to our circuit because it wasn't complete. And now for the short, we'll see something strange happens, because if I start with my red and explore all the paths, the fact that there was no obstruction on that parallel path means I have essentially connected the battery to itself. So this is why the short circuit doesn't cause the bulb to turn on, because you're really just connecting the battery to itself, and the battery is just going to get very hot. Now, you also could color this entirely blue if you started from the bottom terminal. So the potential is not even well defined, because all you're doing is shorting the battery. Okay, so that's our potential model. Compare the brightness of one bulb in each configuration. Justify using the color model. Okay, so, well, we said that the greater the color change across the bulb, meaning red to blue is the biggest, the brighter the bulb. So we actually don't get a lit bulb in the short circuit. So short circuit is dead last because we had no change. And we also know that the simple circuit and the parallel are going to be the greatest because that's the greatest possible change is red to blue. So series just lives in the middle. So we have the short, then we have the series, then we have the simple and the parallel. So in series, this was red to orange, whereas the simple to parallel, and maybe let's use the colors for this. And for simple and parallel, it was red to blue. So the greatest color change you can get is if you get the full battery drop, but series, you had to go through that intermediate step. So that's why the series is not as bright. So that's a nice little conceptual one. Consider the following concepts relating to our microscopic model of electric circuits. How do we define current? Well, we define the current I as just the charge passing through a cross-sectional area per unit time, which is equal to dq dt. Or you could take this as like our average rate of change instead of a derivative if we wanted the average current. So what is current density? So anytime you have a density, it means you have an object distributed over a size, and current is distributed through areas. So we define the current density J as the current within a portion of your cross-sectional area. So we define that as current divided by area. How is the E field defined, and how does this relate to potential difference? So even with circuits, we talked about the E field as being this sort of driving force on charge carriers. So the electric field is the force per unit charge. It gives the direction of force on a positive charge placed at any given location. And it relates to potential difference because the change in potential within your circuit component is equal to the average electric field strength times the distance. So we get delta V equals ED with some sign. So we should take this as an unsigned quantity and know that if you go with the field or with the current, you go downhill. What is drift velocity? Well, drift velocity says that electrons do move randomly really fast in all directions, but if you apply a potential difference, they're still moving randomly and they're still mostly canceling their velocities, but there's a portion that sort of creeps towards one side of the circuit. So essentially we could draw our cylindrical resistor model. And what drift velocity means is I could draw these electrons sort of going in random directions, but mostly they're progressing sort of to the right. So if these were electrons, maybe this would be the positive and this would be the negative end of the resistor. And we'd see that our V drift is kind of roughly to the right here. And it should be noted that this drift velocity is incredibly slow. It's like millimeters per second. Because there's so many of these electrons smashing into each other, but the E field is just sort of progressing them along the tube. We use the analogy of it being like a dog that's barking at the sheep, where the sheep are still kind of grazing randomly, but they're just progressing towards the barn. So we do have a formula. We have V drift is equal to I never. No, that's just not right. It's the current I. The equation is I never, sorry. this is our relationship. This is actually beyond the scope of AP Physics C. We have been told this year. This is our expression for drift velocity. Well, it's for current, but it involves drift velocity. So what we can see here is that the important thing to note is from a qualitative point of view, we could solve for v drift, and we'd get v drift is equal to I divided by NEA, but we know what current divided by area is. That's J. So we'd get J divided by NE. So the main takeaway here is that your drift velocity is going to be proportional to the current density. Which should make sense, right? Because if current represents a sort of rate of change, it makes sense that the drift velocity should be proportional to how densely packed that current is. It's giving sort of the rate that they're progressing through the resistor. And it should depend on the area, because you could have a lot of current, but if your area is also huge, you're not necessarily transporting a lot of charges fast to get that same rate of flow. But again, it's very rare that we'd even ask about drift velocity, never quantitatively. So let's talk about electric resistance. Where does electric resistance originate in our circuit model? Well, we said electric resistance is about sort of the number of collisions or obstructions along your path. You can also think of it as how long it takes to reach the other end. So our formula for resistance says that resistance is equal to resistivity times length divided by area, which should make sense because the resistivity is a material property that's essentially the number of obstructions. The length, of course, it makes sense that if you have to go down a longer hallway, it's going to take you longer. And for area, well, if you have a wider hallway, there's less potential barriers for you to run into. Also think about it as like breathing through a straw. It's a lot easier to breathe through a straw that has a large area. Oh yes, we should also say the calculus version of this. So if we have a resistivity that actually varies along the wire, we can just say that we can integrate all of the little resistivity times length chunks and divide them by the cross-sectional area. And you'll know you have to do that if you get a function, like in C. A cylindrical wire has radius A, and is made with a material that has resistivity that increases according to this function. Drive an expression for the resistance. Now we'll just ignore that there's zero resistivity at one end for some reason. But our formula for resistance, since we have a function, is that we are going to have to integrate the quantity resistivity times change in length divided by area. And this dl is usually a dx. So my resistivity function was rho 0 times x over L, and my dl is dx because I'm moving in the x direction. And what's my area? Well, this is a cylindrical wire, so the area of a cylinder, its cross-sectional area at least, is pi r squared. And it says my resistor bounds are 0 to L for the length here. So we can pull a bunch of stuff out. We would get rho 0 over pi a squared times L comes out in the integral, and then we're just integrating x dx. And that's just a pretty standard integral. That'll just be L squared over 2. So we get rho 0 over pi a squared L times quantity L squared over 2. One of the L's cancels, so I just get 1/2 rho 0 L over pi a squared. And notice this result actually could have been figured out without calculus, because this is exactly half of what you would get if the resistivity was rho 0 the whole way. And since it increases linearly, it has to be the average resistivity would be the average of 0 and rho 0, which would be 1/2 rho 0. So essentially we just said resistance is equal to 1/2 rho 0 times L divided by the cross-sectional area. All right, lab time. Given an ohm meter, which measures resistance, describe an experiment that could be conducted in order to calculate the resistivity of the material used to create the wire segment. So we want to just show how to do that. Now there's two real approaches here, but assuming we have just a set wire, along with other standard sort of lab equipment, you just set up your wire. And then with our ohm meter, you're going to take the resistance. You're going to take the resistance between 2 points along the wire. It's probably best to fix one of the ends and then just move the other clamp along the other end. And this distance we will call X. And you can just slide that sort of clamp along the wire to get resistance of the wire as a function of X. And also what do you need? So you need to measure the area, which is a constant. That's usually printed on there. That's why I kind of went implicit, because wires have this property called their gauge, which relates to the cross-sectional area. So then you're going to measure the resistance R for various X. And of course, the various is how we reduce our uncertainty. So our formula says resistance equals resistivity times length, which is X, divided by area. So this means resistance is equal to resistivity over area times X. So it's actually linear already. So our resistance can go on the X, or sorry, on the Y. Our length X can go on the X. And our slope is resistivity over area. So we can say graph R versus X, and the slope will be equal to resistivity over area. Now I know there's some slope purists out there. I might agree with you that I actually might want to graph resistance versus X over area. So the slope is just my answer of the resistivity. If you do that, great. I just did the most common. Most people like to graph the simplest thing and then do slope algebra. Some people like to do all their algebra to graph some nasty quantity so their answer is as simple as possible with the slope. All right, Ohm's law. What is Ohm's law in macroscopic form and microscopic form? So in macroscopic form, this is what we're familiar with, is just the total current in a resistor is the potential difference across it divided by resistance. And for microscopic form, the electric field strength, the current density. So if we do this microscopically, all we do is we divide both sides of this by the area. It would be our sort of equivalent of what we get when we divide all of these terms. So if we divide current divided by area, we get current density. If we divide this entire right side by the area will cancel with some of the resistivity terms. So we get the applied electric field divided by the resistivity. So we can see that this is sort of just analogous, right? Because on the macroscopic level, we get current, and on the microscopic level, we get the current density. On the macroscopic level, we get a potential difference. What causes potential difference? Electric fields do. We have on the macroscopic level resistance, and what microscopic property is affecting resistance? That would be resistivity. So just like Ohm's law says that current is proportional to the applied potential difference, microscopic Ohm's law states that current density is proportional to the applied electric field. Show how to wire an ammeter and voltmeter to measure the current and potential difference related to a resistor. Well, of course, if we connect a resistor to a battery, you can put an ammeter anywhere to get the current. Just has to be in the loop. And then for our voltmeter, we just have to attach it in parallel. Because remember, potential difference is the height difference between 2 points. That's why there's 2 probes, each on one end of the resistor. So remember that the ammeter for current goes in series, and the voltmeter for potential difference goes in parallel. All right, sketch a graph of the current through a material as a function of the potential difference in each of these cases. Well, let's say your material follows Ohm's law. So we apply different potential differences and get some currents out. Well, if the material follows Ohm's law, we are, of course, going to get a nice linear function because we're given that it is directly proportional. What if instead the material doesn't follow Ohm's law, and the resistance actually increases as you apply more and more of a stronger potential difference? This is a more realistic model for a light bulb. In reality, light bulbs are not ohmic because that filament heats up, creating more resistance. So you could think about this as that if I apply a small potential difference, I'm going to get a pretty significant gain in current. But if I keep going out more and more and more, I'm sort of getting diminishing returns because resistance can be thought of as like how much extra current are you getting per volt. So you actually get a concave down function when resistance increases like this because you're getting less bang for your buck as time goes on, because this is your input, your delta V, and this is your output. So you're getting lower increases in your output, meaning the second derivative must be negative. If the material follows Ohm's law, how can we calculate resistance? Well, it's important that we graph this. This is the relationship that we like to graph in College Board problems, at least, because this is more like on the experimental side. Like, you can't just choose the current through the circuit. That's not usually a thing you can do. But what you can pick is you can modify things on the right side, because you can pick different battery voltages, you can pick different resistances. So just for a cause and effect relationship, it's more proper to set up Ohm's law this way, which is why this is usually the thing that's graphed. So if you're forced to look at a graph that looks like this, you'd be given the current can be written as 1 over R times the potential difference. So that means our potential difference on the X, our resulting current is on the Y, so of course our slope is 1 over R. So the slope from an Ohm's law graph is 1 over the resistance if you graph current versus potential difference. Now, of course, if you're actually doing a lab, you can totally just reverse the axes so your slope is R. Yeah, there's nothing wrong with that. But this is usually what data we're given, because we tend to stick to that middle school idea of your independent variable, the one that you change directly always goes on the X. So that's why we're usually given this set of axes, even though we have like an extra step to do for the slope. All right, consider power. What is the definition of power? Well, power, going back to mechanics, is just the rate of energy input or output. So if we want to think about what that is for a circuit, we could think of power as the energy change, the energy that's sort of given to each charge, times the amount of charge that flows through your circuit every unit of time. And of course, we wrote it this way because we have expressions for each of these. Energy per charge is what we define as our potential difference, and charge per time is current. So we can write power as current times potential difference. So this is the definition of power for a circuit component. And if Ohm's law works, we can start manipulating and do some other things. So assuming this material follows Ohm's law, we can derive expressions for power by just substituting. Well, Ohm's law says that delta V is equal to I times R. So our second power formula could be I squared times R. We would do that if we know things about the current, but don't necessarily know potential difference. Or if we didn't know the currents, this is actually the more common case because you're usually given potential difference related items. We would get the not centripetal force, or sorry, the not centripetal acceleration version of power, where we get V squared over R. So all of these are equivalent assuming we have an ohmic material, which we always do. But they're just useful in different scenarios. So it depends what info you know. There's nothing wrong with just only believing in I delta V, by the way. This is the only one on the formula sheet. It is very useful to just know the other two, though. So how can the total energy dissipated over a time interval be calculated? Well, we know that power is equal to energy divided by time. So this means energy would be equal to power times time if we have constant power, which we do in a lot of like just simple circuits, but we also deal with a lot of time varying circuits. So instead we have to find the energy change by taking the amount of energy dissipated at a moment times a small moment in time, and then we add all those up. So usually we're going to be using this sort of integral definition of power. Here's a case where that happens. So suppose we have an increasing current through a resistance R that is quadratic. We want the power, and we want the total energy dissipated. So here's a case where we want one of those alternate power expressions, because I know R, I don't know V. I could totally find it. V is just IR. But we said that power is equal to I squared times R. So our current is alpha T squared. So we got to square that thing, multiply by R. So we get alpha squared T to the fourth times R. So I might just write this as alpha squared R times T to the fourth, just to show the functional dependence. Total energy dissipated on an interval. Well, anytime you see an interval, you know there's probably an integral that's gonna happen. So our total energy is just all of the tiny energy contributions, power times time. So we're going from 0 to capital T. Our power is just alpha squared R T to the fourth. And this junk is all constant. T to the fourth integrates to 1/5 T to the fifth. So we get alpha squared R capital T to the 5 all divided by 5. All right. Consider combining resistors in a circuit. How do resistors add in series? Why does resistance increase by adding resistors in series? Well, we know that R in series is just addition. And this effectively increases length. So that's why resistance goes up, because we said R is equal to rho L over A. So if we're effectively doing a series, we're just making the circuit longer. So of course, series resistance goes up. Now in parallel, it's the opposite, where if some quantity combines via addition in series, that means in parallel it must combine using the reciprocal relationship. And notice here, like R is still rho L over A, except now in parallel, you're giving your current another path to pick, so it has more area that it could traverse. So you're effectively increasing the area. In series, what's the same current or potential difference? Well, if there's one path for current, the current can't go anywhere. We call that charge conservation. Series is the same current because charge cannot just vanish. What about parallel? Well, in parallel, we get the same potential difference because of conservation of energy. Because we know that potential relates to energy change. And if you can get back to the battery in both paths, you must have the same energy change, or else your color coding wouldn't match. So this is easier to think of with the color model, because just try to color it. You'll always get the same color change in parallel, and that relates to energy. Because we said that potential is sort of our electric height. All right, consider the two resistors shown below that are connected to a battery of EMF script E. Both of the resistors are made of the same material and have the same length, but resistor Y has twice the area of resistor X. So we're going to do a huge comparison here. Notice this is a series circuit, so that tells us some things. We have the resistance R of each cylinder that we're comparing first. So it's the same length, same material, but Y has bigger area. So this means X has larger resistance than Y, since the area of Y is larger than the area of X. Because the larger your area, the lower your resistance because of rho L over A. The current I through each resistor. The current is actually going to be the same because current is the same in series. So what does the size affect? Well, the size is going to affect the current density. So we have two resistors. They receive the same current because you can't just vanish the amount of charge. That charge, all the charge flowing through X must also go through Y, but it gets spread out more in Y. So the current density is higher in X, since same current is distributed in each area, and the area of Y is larger. Because you're basically dividing by a bigger number. That's why the density is higher in X. What about drift velocity? So drift velocity, we said, is just proportional to current density. So the drift velocity is higher in X than it is in Y, since Jx is greater than Jy. Another way to think about that, because we said we did say that V was proportional to J, but another way you can think about it is these have to create the same current. And current you can think of as being at least related to how fast these charge carriers move. So if you're cramming these charge carriers in a smaller area, they got to move faster to generate the same flow rate. Think about it as water through a pipe. If these are pipes and they're pumping the same number of gallons per second, you don't have to be moving the water as quickly through the big pipe to get the same volume. What about the electric field strength within each resistor? Well, this is the same argument again. We're going to have a larger electric field strength in X, since the current density is higher in X. This is Ohm's law, because we said that electric field strength is proportional to current density as well. Same idea here. Same idea here. Potential difference across each resistor. Well, this is a series circuit. They receive the same current. So delta V across X is larger than delta V across Y, since the resistance of X is larger than the resistance of Y. And we know that because delta V is proportional to the current, which is the same. Or sorry, it's proportional to resistance under the same I. So let's just say delta V equals IR. And this quantity is the same for each. All right, now let's do some deriving. The equivalent resistance of the circuit. Well, we have two resistors in series, so we just need to add them together. So our EQ is just the two resistances added together. X had length L and area A. Y had length L and area 2A. So we get 1 plus 1/2, which would be 3/2. Rho L over A's worth of resistance. All right, what's the current in the circuit? Well, the current in the circuit, we have our lovely Ohm's law relationship that says I total is equal to the battery EMF divided by Req, which is equal to the battery EMF script E divided by 3/2 rho L over A. So we get some flipping around, so that 3/2 becomes a 2/3 script E times A divided by rho times L. All right, power by the battery, pick your favorite. We actually just solved for current and we know the EMF. So I'm just going to say that the total power is equal to the total current times the battery EMF. So I just tack on an extra script E there, which gives me the quadratic dependence that I expected. Yeah, kind of a tricky one. This is one of the harder ones from the circuit section, especially comparing all these macroscopic and microscopic quantities. Kind of some subtlety here. I think the drift velocity one is definitely tricky. All right, now it's time for some plug and chug circuit garbage. Kirchhoff's rules. State Kirchhoff's voltage rule, also called the loop rule. Why is this true? The loop rule just says the sum of all the voltage gains / drops around a closed loop is 0. This is just conservation of energy, because any potential energy change across the battery is eventually made up for through those drops. This just says you got to go from red to blue somehow in your circuit. What does the current rule say? Current rule says total current in equals the total current out of a junction. You can't just vanish current. That's where those come from. Here's a really cool item I wrote for my physics 2 test that uses both of Kirchhoff's rules. I think this is a really cool question. Calculate the resistance R in the circuit below, given the current at Y is 0.5 amps. Anytime you learn a circuit number, you should probably fill it in. And the current at Z is 1.5 amps. So I think it'll make sense just to bring that 1.5 amps sort of above its branch there. So this uses both of Kirchhoff's rules. So we have this resistance R that we wish to find. So we also know that we're going to have some sort of total current there. So we can say that the total current must be equal to, well, that current is going into this junction point. Which is equal to 0.5 amps plus 1.5 amps, which is 2 amps. Because we know to get this resistance, we know that we need to solve some sort of Ohm's law equation, delta V equals IR. So we got to get delta V, which is a loop rule item, and I, which is a junction rule item. So we have successfully done the junction rule because we see that these are our junction currents that split off. So they must have been 2 amps originally. Now what's going on here with the bar chart? Well, we know we're going to use the fact that delta V across the resistance R is equal to the current through the R resistor times the resistance. So we know that the resistance is just going to be delta V divided by I. So we need the potential difference across just the resistance labeled R. So if we color coded our potential here, we would see this is the circuit we end up getting. So X is sort of our red color, would be 12 volts. Y is our intermediate potential, which is our orange color. And Z is at our low potential color, which is blue. So we see that the potential difference across R is just whatever that delta V is. It's whatever that delta V is to get from red to orange, which is 12 minus 8, which is 4 volts. So this means our resistance is just 4 volts divided by 2 amps, which is equal to 2 ohms. So nothing too crazy there. Just kind of looking at both of Kirchhoff's rules together to get us that answer. All right, now we got some combining to do. So this is just a sort of routine computation. So we want to just calculate everything going on in this circuit. So if we color code it, this combination circuit ends up looking like this. And we want to find all the values. So we do know that low potential is going to be 0 volts. High potential, the battery steps us up to 18 volts. So this orange color is something in the middle. Probably not 9 though. So the first step is always try to get your total current. Because if you get your total current, you can find the voltage drop across anything in series. So we can do that by getting equivalent resistance, because we know that I total is defined as the battery EMF divided by the equivalent resistance. So what is the equivalent resistance here? Well, the 3-6 parallel combination, this adds via the reciprocal rule. This is one that we should just kind of be familiar with at this point. It's the smallest nice number one that works out all the time. So actually the 3 and the 6 make 2 ohms together in parallel. 3 plus 6 equals 2, as we like to say. So we have a 2 and a 4, which makes 6. So REQ is equal to 4 plus 2, which is equal to 6 ohms, because the 4 is in series with the 3 and 6 parallel, which combines to 2. So 4 plus 2 is 6. Our battery voltage was 18 volts. We divide that by the 6 ohms, and we get 3 amps of total current. So that is very helpful to us. All right, so we've learned some things, so let's put them in the table now. So we have learned that our equivalent resistance was interesting. Oh no, yeah. Our equivalent resistance is actually 6 ohms. Our battery voltage was 18 volts. Our battery current was 3 amps. And power is equal to I delta V. And we know I and delta V, so we can just multiply. So we get 18 times 3, which is, let's see, 24 and 30, so 54. And that's in watts, because it's joules per second, which is a rate of energy. All right, so now we can do some computing. So first of all, we can find this delta V, because delta V from Ohm's law is I times R. So our current is 3 amps, our resistance is 4 ohms, so that's 12 volts, IR. So we have learned that. Through the 4 ohm resistor, we get all 3 amps of current, and we have dropped 12 volts. So our power dissipated, 12 times 3 is 36. All right, so now what's going to happen, though, is our current is going to reach the junction point, and it's going to split. So we can't just multiply 3 times 3 and 3 times 6, because the current splits off. Now, you could reason how it's going to actually split, but we have to use the loop rule here, because loop rule says that if you gained 18 volts from the bottom to the top, you must drop 18 volts on your way back. So I'm at 0 volts, 0 volts, I'm at 18, then I drop 12. So what is 18? Drop 12, 18 minus 12 is 6. And then I'm dropping from 6 to 0, which is of course 6. So if I drop 12 volts across the first resistor, I must have dropped 6 volts across the others. And again, the 6 ohm also shares that 6 volt, because that's also a complete loop. Parallel, same voltage, we can see by the color. So I've actually learned that the voltage drop is 6 volts across the other 2, which tells me that my current through, we can just find that via Ohm's law, because current is delta V over R. So how do I make 6 volts? What do I have to multiply 6 divided by 3? That's 2 and 1. So our powers here would be 12 and 6. And we can actually check that we did it right, because, first of all, we know the loop rule works because we use the loop rule to get all our voltage drops. And we also know the junction rule works because we said this current was 2 amps and this current was 1, and it does add up to the 3 that went in. And we can also check the powers energy conservation because 36 and 12, that makes 48. 48 plus 6 is 54. So our total power in from the battery equals our total power out from the 3 resistors. Now we have a conceptual Kirchhoff rule question. So we have this combination circuit. It's pretty similar to the last one by design. We want to rank the current I through each resistance. Justify your answer without performing any derivations. Well, of course, we're just going to do a quick potential coloring speed run here. So again, we can see that, first of all, what is the current through each resistance? Well, we know that we're going to have some sort of current, some sort of total current I that hits the R resistor. And then what's going to happen is the current is going to hit this junction point, and the current is going to split, where you're going to get some of the current through the 3R and some of the current through the 6R. But also, think about this with our drive-through analogy. We know that the voltage drop is the same because the color change is the same, but one of the resistances is higher. So are more people going to go through the high resistance path or low resistance path? Well, of course, more are going to go in the low resistance path because you don't need as much current to create the same voltage drop if you have a large resistance. So again, the thing that must be the same through the other 2 resistors is IR. So if you have a bigger R, you must have less I in order to compensate. So we can say that our ranking is I is greatest through the 1R, then the current splits, and there's more of the current in the 3R versus the 6R. And we can also figure out exactly how that splits into ratios. This is just me saying that resistance full current, the potential difference is the same across the 3 and 6, so less current is needed through the 6 for the same potential difference. We can also figure out the ratio, because if the 3R is exactly half of the 6R, we're actually going to get 2/3 of the current goes here and 1/3 of the current goes here, because we know exactly twice as many customers must go down the fast lane because it's twice as fast. So this receives like the battery current I, this receives 2/3 of the battery current, and this receives 1/3 of the battery current. Alrighty. Rank the potential difference across each resistance, justify without derivations. So there's an easy part and then there's a hard part. So the easier part with potential difference is just looking at this picture and knowing for sure that it's the same across the parallels, because it has to be. But is it bigger or smaller than the potential difference across the primary resistor before the splitting? So here's where we have to use the fact that delta V is equal to IR. So we do know that, for example, the potential difference is the same. So if we can figure this out through one of the resistors, we get it through all of them. So we know the potential difference across this resistor would be IR. That's this potential difference. So if we find one of these potential differences, we can figure out how they compare. And we said that 2/3 of the current goes down the 3R. So we'd get like so delta V across the 3R. I know we're kind of breaking our deriving rule. I think it's worth it here. Delta V across the 3R would be 2/3 of the battery current times the resistance 3R, which is actually equal to 2 IR. And now this is super easy to do if you do equivalent resistance. And I think that's a much better solution. I just thought it was less derive-y if I didn't combine these, because it's actually super easy to see that this voltage drop has to be bigger than this one, because if you combine 3 and 6 in parallel, you get 2. And then you're just left with a 1 and a 2 in series. So you can see that this combination has bigger resistance than first, because if you combine them, you no longer have to deal with the splitting aspect. So here's that kind of winded explanation where we're going to say that the 3R and the 6R tie because of the parallel rule. And those actually, since they have a larger equivalent resistance, they actually do beat out the lone singleton resistor. So the parallels have the same voltage drop. The total current splits. So there's a 2-to-1 ratio with the currents. 2/3 goes through the 3R, 1/3 goes through the 6R. Each of those products is greater than IR for the first resistor, so we know there's a bigger potential drop across the parallel combo. Yeah, not easy. Of course, you could totally just work it out. You would see what the total current is, and you could work it out where this is 1/3 of the battery voltage and 2/3 of the battery voltage, and it all works out nicely. But wanted to stretch our conceptual thinking a bit. All right, circuits with multiple batteries. What are the rules for loop equations? Well, our loop equation is something of this form. Sum of the delta V's is 0. Potential difference is positive when you go from minus to plus, and potential difference is negative IR when traveling with the current. So let's write a loop equation for the circuit shown below. So I'm going to say that my sum of my delta V's is equal to 0. We'll say that I'm going from negative to positive. We're going to go this way. If you go the other way, all of your signs disagree with me, but it is the same equation. So first, I encounter a battery where I go from negative to positive. So I've gained script E1. Then I'm going with the current. So I lose some potential across that resistor. And then I'm going from positive to negative through this battery. So that's actually a potential drop. So this is our loop equation. Now, it should make sense that the batteries are being subtracted because these batteries are fighting each other. So the direction of current really depends on which EMF is larger. Write 3 unique loop equations and 1 unique junction equation for this circuit. Okay. So first, the easier one is to get the junction equation. Because we can see that for a junction equation, we see that I1 and I2 are going into this dot, and I3 is coming out. So we can say that for the junction equation, I1 plus I2 has to equal I3. Now, these current directions could be completely wrong. If you solve these and get a negative sign, that's totally fine. Like, we're just going to live with the sign convention here. And now for the loop equations, we just have to pick a few loops and commit to them. So let's see what happens. I'm going to start with like the outer loop where I just box in the entire circuit. So that's going to look like I gain some voltage across the first battery. Then I go with the current, so I drop across the first resistor. And then I go from positive to negative across the second battery, so that's a subtraction. So this actually looks very similar to the previous loop equation we wrote because it's sort of that same thing where we're going through these two batteries of opposite orientation. Then maybe let's pick my innermost loop. Yeah, I'll do the complicated one last. This is the simplest loop equation, is if I go, so I go through this one. So if I do that, depending on which way we go, let's say I gain some voltage across my battery, but this time I'm actually going opposite the direction of current flow. So it's not a plus IR, it's actually not a minus IR, it's actually a plus IR through that one. Telling us our direction of current is probably wrong there. So again, why is this plus? Well, yes, I went from minus to plus to this battery, but I'm going against the current, and current flows to low potential, so that actually must be high. So actually, it might be helpful to label that the current sort of points towards like which end of the resistor is positive versus negative. That's probably a good thing for you to do, actually, is to label all these, that you know the current points towards the negative end of each. And then we can do sort of this complicated loop here where we do that one, where we gain some voltage across the battery, we drop some voltage across R1, and then we actually gain some voltage when we go through R2 because it's against the current. That's among the trickiest aspects in this circuit unit for sure, is these sign conventions. Now, solving these, you would not be expected to solve these, but absolutely you should be able to write Kirchhoff loop and junction equations like this. All right, and just about an hour too. That's right on pace. All right, unit 1 is complete.